In statistics, first hitting time models are a subclass of survival models. The first hitting time, also called first passage time, of a set with respect to an instance of a stochastic process is the time until the stochastic process first enters. More colloquially, a first passage time in a stochastic system is the time taken for a state variable to reach a certain value. Understanding this metric allows one to further understand the physical system under observation, and as such has been the topic of research in very diverse fields, from economics to ecology. Examples. A common example of a first hitting time model is a ruin problem, such as gambler's ruin. In this example, an entity has an amount of money which varies randomly with time, possibly with some drift. The model considers the event that the amount of money reaches zero, representing bankruptcy. The model can answer questions such as the probability that this occurs within finite time, or the mean time until which it occurs. First hitting time models can be applied to expected lifetimes of patients or mechanical devices. When the process reaches an adverse threshold state for the first time, the patient dies, or the device breaks down. First passage time of a 1D Brownian particle. One of the simplest and omnipresent stochastic systems is that of the Brownian particle in one dimension. This system describes the motion of a particle which moves stochastically in one-dimensional space, with equal probability of moving to the left or to the right. Given that Brownian motion is used often as a tool to understand more complex phenomena, it is important to understand the probability of the first passage time of the Brownian particle of reaching some position distant from its start location. This is done through the following means. The probability density function for a particle in one dimension is found by solving the one-dimensional diffusion equation. Namely, given the initial condition, where is the position of the particle at some given time, is the tagged particle's initial position, and is the diffusion constant with the SI units. The bar in the argument of the instantaneous probability refers to the conditional probability. The diffusion equation states that the speed at which the probability for finding the particle at is position dependent. It can be shown that the one-dimensional PDF is this states that the probability of finding the particle at is Gaussian, and the width of the Gaussian is time dependent. More specifically, the full width at half maximum, technically. This is actually the full duration at half maximum as the independent variable is time. Scales like using the PDF one is able to derive the average of a given function at time, where the average is taken over all space. The first passage time density is the probability that a particle has first reached a point at time. This probability density is calculable from the survival probability. Consider the absorbing boundary condition. The PDF satisfying this boundary condition is given by 4. The relation between the survival probability and the FPTD is as follows. By using the diffusion equation and integrating by parts, the explicit FPTD is the first passage time for a Brownian particle, therefore follows a LE acute Vy distribution. 4. It follows from above that where this equation states that the probability for a Brownian particle achieving a first passage at some long time becomes increasingly small, but always finite. The first moment of the FPTD diverges, therefore one cannot calculate the average FPT, so instead, one can calculate the typical time. The time when the FPTD is at a maximum model has two underlying components: a parent stochastic process, and a threshold. The first hitting time is defined as the time when the stochastic process first reaches the threshold. It is very important to distinguish whether the sample path of the parent process is latent or observable, and such distinction is a characteristic of the FHT model. By far, latent processes are most common. To give an example, we can use a Wiener process as the parent stochastic process. Such Wiener process can be defined with the mean parameter, the variance parameter, and the initial value.